Hi, today we're going to be looking at this medically rated isolation transformer. This is a 1000 volt amp model from REO Inductive Components, and I picked this up from eBay about a year and a half ago for probably about a tenth of what they go for new. Although it is effectively new, I couldn't even see any signs of it having been used. And I've been using this at my bench for quite a while now. But one major annoyance I have with it is that it only has IEC connectors on the front. So I bought a few MK double sockets. These are metal clad, so they're really well made, pretty solid, and I'm hoping to be able to fit this on the top here if there's room inside. And then I've also got some 4mm banana jacks, the safety type, which hopefully I can add along the side here. So the other minor annoyance with this transformer for my purposes is that the earth pin of these connectors is permanently connected to mains earth, and also to this earth stud here. So on medical devices these earth studs are pretty common, the reason being that you want to minimise the potential between electronic equipment, and so what they do is they have an earth stud on all the devices and an equipotential earthing bar in, say, the operating room, and you connect all the devices together, and then if you're touching two different devices there's a very low risk of any touch potentials between the devices, which could lead to high leakage currents through the patient. So what I want to do is possibly add either another banana jack, so we have incoming mains, earth, and then the earth to all of these connectors and the socket as well, or maybe just add a switch so we can connect or disconnect mains earth. So the first thing to do is, this is riveted closed, so I'm going to drill these rivets out. We'll take the cover off and have a look what's inside. I suspect there's more than just the transformer in here, because when you turn it on you can hear what sounds like a contactor inside, so it may well have some soft start circuitry. But anyway, I'll drill this out and have a look. Right, so I've just moved out to the garage. I've put a 3mm drill bit. These look like 3mm rivets, so I'll just take it slowly because I don't know what's underneath the cover. I don't want to accidentally drill through any wires. Right, I'll just give this a quick vacuum up, and then we'll take a look under the cover. Okay, so now all the rivets are out. Let's have a look. Oh, looks like I'm bleeding. Nice. Now all the rivets are out, let's have a look inside. So there's an earth lug on the side. Let me just undo that. So I just needed to disconnect the earth lug from the top panel, but now we can remove that completely. So what we see is immediately a very large toroidal transformer, which has been potted as well. Looking at the label, this has two 230 volt windings. There's also an earth cable going in there, so we'll see what that's connected to. And then it did sound like there was a contactor inside, and yeah, there is one here, what looks like a timer of some kind, and then down here there's a series of NTC resistors which presumably do the inrush limiting. So there's a dial on the top of here. It's reading 0 to 10. It's currently set to 3, and I assume that's probably hundreds of milliseconds. It's set to 3 at the moment, so it probably delays the turn on of the contactor by 300 milliseconds, but we can have a look. So if I just plug in the mains to the input jack and turn it on, so I'm turning it on now. Yeah, that seems about, it's definitely less than half a second. I don't know if you can see that, but some of these screws are actually moving when the contactor clicks in and out. Those don't appear to have any terminals in there, any wires in the terminals, but it's probably worth just doing those up so they don't come loose and end up rolling around inside. But we can just check. So if I set this dial to 10, that's probably the equivalent of 1 second. So if I turn it on now, yeah, that seems about right, so that's about a second. I don't know if they calculated 300 milliseconds from anywhere. Maybe that means that the rating of these NTCs can't be exceeded even if you have a load plugged in. I don't know, but I'll set it back to 300, that seems fine. So next we'll have a quick look at what this earth wire is doing, and then we'll see how we can fit the 13 amp socket into the top lid. Okay, so that's about as good as I can get on the label here. So we can see there's a primary with a thermal fuse, which on the label I think it says 100 degrees, so if the temperature of the transformer exceeds 100 degrees centigrade, then the transformer is probably ruined because there's no way you'll be able to replace that thermal fuse. And the earth is connected to a shield between primary and secondary for additional safety, so it's not connected to any windings, so we're all good there. So I think it's quite difficult to see on camera, but there is a earth wire at the bottom. It looks like they've just got normal PVC coated earth cable within a silicone kind of sheath. You'd normally do that for heat resistance, but I guess they're trying to add an extra barrier of isolation here. But there's an earth wire which goes from the incoming IEC to the 3 sets of outgoing IEC connectors, and then onto this main earth lug here, which is then connected to the flying lead, which goes to the top cover and then also to the transformer. So we will have to rewire this portion so that I can isolate these from the mains earth if I want to. So next I'll have a quick look at how we're going to get this socket in place. It's fairly slimline, so I think this does look like it can sit here, and then we'll just have to check that these banana jacks aren't going to go too deep. So we'll have a look at the side of that and see what kind of clearance we've got. Here we have the transformer side view, and if we put the 13 amp socket flush with where the top cover would go, you can see we've got quite a reasonable amount of clearance. It's at least 15 millimeters, so nothing to worry about here. We can go right to the edge and we still won't hit anything along the front, and we just have to make sure that we don't hit these wires from the transformer. But other than that, the twin socket can go wherever we want. And then if I just place a ruler across to give an idea of the kind of where the top panel would go, if we've got the banana jacks, that's flush with the top panel. We've got a reasonable amount of clearance here in line with the AC inlet, but if we go too far towards the other end of the transformer, we'll hit the contactors, and if we go too close to the front, we're going to hit the spade terminals from the power switch and the incoming IEC connector. So we just need to make sure that we're in line with that switch, and then we can fit 3 the live, neutral and earth banana jacks in line here, no problem. So I'll just start measuring out on the top panel where I'm going to cut, and just double check all the measurements, and then we'll try and cut that out. So I've just put some masking tape onto the top cover to mark where the transformer kind of is, and the keep out zones, so we can't really go any closer to the front than this line, or any further back than this line across here. And it looks like the socket should quite happily sit just there. And then we've got four 4mm banana jacks here. So we've got neutral and live. Of course, it's not actually neutral or live because it's not earth referenced in any way, so that's just the output from the secondary of the transformer. And then we have the mains incoming earth here, and then the earth to the 13 amp socket earth pins, and also the IEC connectors on the front panel. So I'll just mark out exactly where I'm going to cut now I've decided on the positions, and then we'll probably cut the shape out for the socket with a jigsaw, and then we can just remount these banana jacks, because I think they're 12mm mounting hole, which is probably a bit bigger than you want to do with a standard drill bit. So I'll use one of those cone shaped stepped drill bits to drill those out. So I've marked out where we need to cut We've got the 4 holes here for where the banana jacks are going, and then we're going to cut around this profile here, and basically what we're going to do is we're going to sink the socket in flush with the top panel, so we do have to provide a means of allowing it to be screwed in. So there's a mark here and here for where we're going to provide a hole. We'll probably, since there's rivets everywhere else, may as well rivet the socket in as well. So we'll just cut around here, which matches with the profile inside the socket, and that should just hold it in place. Okay, so I'm probably going to get told off for doing this in the house, but it's a bit cold outside, so let's centre punch the holes. And this is just one of those automatic hole punches. You don't need to bang it with a hammer, you can just press on it and it gives quite a good keying for the drill bit. So I think I've just finished cutting that hole now, and the socket seems to fit perfectly. So I'll just clean up the area and then we'll get on to wiring it all up. So this is the back of the 13 amp socket which I'm planning on mounting to the top of the transformer. And you can see we've got the 2 earth terminals here. We have 2 just in case the socket's going to be used in an application that needs high integrity earthing. So that's typically kind of IT environments where there's a relatively high earth current all the time from the leakage through the filters on the switch mode power supplies. And you can see that the earth terminals are connected via a strip to the earth connection on the actual socket, but then also to the lugs on the where the screws go through to normally to earth the metal pattress that would be in the wall as well. But obviously I want to be able to isolate the mains earth from these sockets, but I'd still do want protection on the transformer case from becoming live. So I think I'm just going to have to chop along here, probably with the Dremel again, just chop these to disconnect that. I'll probably actually cut along here, and then the same the other side, so there's a bit of clearance as well. So I'll just do that now. Okay, so I managed to cut away the strip here on both sides, so now the front cover is completely isolated from the earth terminals here. Okay, so we've got the meter on continuity, and if I just hook in the probe onto the front here and we touch here, we can see we've got no continuity whatsoever. And then if I just touch the front panel the other side, we have a good low connection. So the mounting screws that I use to mount the socket to the front cover should provide adequate earthing of the actual plug itself, but the earth terminals of the socket I can then loop out onto the banana jack on the top cover of the transformer. So I'll just attach this to the top cover. We've got some shake-proof nuts here, some washers, and then some M3 screws. Traditionally, the UK sockets actually take M3.5 for the metal pattresses and the various accessories that you can screw this into, but I've no need to use the official size here. 3mm will be fine. And it looks like with these binding posts you can just get your grips onto the chamfered edges here, and then hopefully you should just be able to do the nut up with some pliers. That stops it twisting as you're trying to tighten them up. So I thought it was just worth spending a moment explaining what it is I'm trying to achieve with the wiring inside the isolation transformer. Here's a drawing of effectively what we have inside the box. We have the incoming mains connection, a double pole isolator, some soft start circuitry, the isolation transformer itself, and then we have our new 13 amp socket, the existing IEC outlets, and the 4mm banana sockets on the top of the unit. So what the unit previously had was the incoming earth connection connected directly to the chassis, connected to the binding post on the front of the unit, to the shield between the primary and the secondary, and then it did previously go directly to the earth pin on the IEC outlets. Instead, what I'd like to do is bring the earth out to the 4mm earth pin on the top of the unit, and then the earth pins from the 13 amp socket and the IEC outlets brought out onto a second earth connection on the top of the unit. And then if I did want mains earth for whatever reason on the outlets, I could just link these two banana plugs together. Or if I wanted to emulate a standard mains connection in the UK where earth is at the same potential as the neutral pin, I could link out the neutral connector with the earth output here, and it would appear like a standard mains connection, but we'd have our full isolation provided by the transformer. So we'll begin wiring up the unit next. So when you're using these crimps, you should make sure that you're using a good quality ratchet crimp tool, but also there's a correct way to insert the crimp into the tool. So you can see possibly on the camera just the bottom part of the crimp has a slightly different pattern to at the top, and also the top part of the crimp is compressed slightly more than the bottom part, which is just providing strain relief onto the PVC sheath, whereas the top part's actually crimping the copper onto the lug. And on the crimp tool itself, you should be able to see that there's two sections to the die. At the rear end, you can see it's actually protruding slightly lower than at the front, and the bit where it's going to compress it slightly more is the bit that you need to place onto the metallic area of the crimp. So in this scenario, the crimp sits this way round when you're inserting it into the tool. Now these binding posts actually have quite a lot of different parts to it. There seems to be 2 washers, a shake-proof washer, and 2 nuts to each connector. So I think the way that they had it was they had 1 nut right down at the bottom. I'll just tighten that up. Then 1 of the washers, and then we put our crimped connection on top of that, and then we have we actually have the shake-proof washer on top of that to make sure that it digs into the crimp that you're using. Another washer here, and then finally another nut on the top here, and that provides a really good mechanical and electrical connection to the binding post. That's actually sheared off, which is slightly annoying. So I'll probably have to attach the earth connection onto the screw that I'm using to hold the 13 amp socket onto the front panel. and just make sure to use one of these shape-proof washers that actually digs through the paintwork and provides a good earth connection. So I'll just do that now. So what we're using here is just some bootlace ferrules. These are twin input ones, so that we can get 2 wires into there and crimp them nicely into the connector. So there we have our wiring ready to go into the lower part of the transformer. That's all nice and tight. Nothing there should come loose. So I've just been having a look at the wiring inside this unit, and I do want to separate the outgoing IEC connectors from mains earth. Obviously that wants to go to that binding post on the top cover that I wired up, but it looks like they assembled it whilst wiring it up, so you can't get to all the connections very easily now. But this is the back of the IEC inlet here, and what I want to do is see if I can crack this hot glue so I can pull this spade connector off. So that looks like it's out now. So if I can find a replacement spade, I think they're called fast-on connectors to go onto here, I can provide a new earth terminal from the incoming mains, and then once I've undone the other end, these IEC outlets will be floating, and they'll be connected to the 4mm binding post on the top cover. So we appear to be in luck. I have some of these crimp terminals. They are uninsulated, so either I can cover it with a bit of heat shrink, or as it is earth, we can possibly just leave it disconnected. And I have also got the crimp tool for this, so we can wire up a new earth wire onto the mains inlet. Yeah, that's the correct size to go on there, so we can cut that kind of to length, and I'll feed that through underneath here. And push that onto there. So that's that sorted. I'll probably put some heat shrink over the end of this, just so it's not hovering around. In fact, what I think I'm going to do is I'm going to cut the crimp off and actually crimp on one of these through crimps, and then the earth from the top cover I'll just connect onto here, and that will provide the earth connection onto these IEC outlets. Okay, so you can see I've managed to just get a crimp on the end of that. So here's the other side of the transformer. This is where all the earth's connected to in a star kind of configuration. What we're going to do here is this is the earth cable that I just connected to the AC inlet. That's obviously going to go to that star point, and also the core of the transformer is also going to be connected to that point. We'll disconnect the earth connection that did come from these IEC connectors from here, and then also we'll take a new wire from this point up to the top cover onto the banana jack that we can then link in if we do want the outlets to be earthed. So that's the 4 earth points tightly tied to the chassis here, and what's left to do is to connect the earth for the front IEC connectors and also the 2 line conductors. I'm not quite sure the best way of doing that yet, because the wire that comes from the transformer just kind of goes under here fairly tightly. There's not really enough slack to kind of join onto those, so possibly I could solder the wires onto the back of these IEC connectors. It's not ideal, as it doesn't provide any strain relief, but we could could cover them in hot glue and make sure that these wires are tightly bound with the wires going across these contactors here, so that it doesn't, so there's no strain on those wires anyway. So I think I'll probably go with that. So polarity doesn't really matter since this is a floating supply, but we'll follow the standard convention of these connectors and have the live going on this side and neutral on that side. Then we'll just see if we can solder those onto there. Okay, so off camera I've just managed to solder the live and neutral coming from the top cover onto the IC outlets. I've also put a bit of hot glue on the top as well, and I don't know if you can just see slightly further along, just along here, I've clipped it to this bundle of wires that's tightly bound onto the contactor and timer. Also, the earth connection from the top cover that goes to the IEC outlets has been connected to the the barrel crimp that I had the other side, and obviously we've got the earthing point just here, which has the incoming mains, core of the transformer, the front binding post, and also the 4mm jack on the top cover. So the next thing to do before we power it up is to test it. So I'll just go and get my insulation tester and we can see if it's all connected up correctly. Right, so I've just temporarily put the cover on the transformer, and we've got here a continuity and insulation tester which I've just nulled out the test leads on. So we just want to make sure that our incoming earth connection is connected to the chassis correctly. So I've just put this on the binding post at the front, and if we press test here, we see we've got a nice low reading of 0.03 ohms. We can also just check that the top cover also has continuity, and that's also quite good. We'll just test it in here as well, and that's also okay. Next, we probably want to do an insulation test just to make sure that we haven't compromised the insulation between the incoming mains and the chassis. So I'll put this across the two line conductors and across earth, and we'll put it on insulation test mode, and this will put 500 volts across and measure the impedance. And we can see here it's reading greater than 999 megohms. So we haven't compromised the insulation resistance here at all. Also, we probably also just want to check that the earth of the actual socket itself isn't connected to chassis. So we can connect this onto the chassis point here, and this is just a special test lead which goes to the socket here, and if we test here we can see we have no continuity at all between the earth pin and the chassis. So that all seems in order, so we should just be able to turn the device on now and check it behaves as expected. Okay, so I've just connected the mains and I've just turned on the transformer. We've got the output connected to the Fluke 289 on AC volts, and we can see that we're reading 242 volts, which is what we'd expect. Now, what we do have inside the transformer is we've got our primary, which is connected to the incoming mains. We also have the earth, which is connected to the core of the transformer, and then also goes out to the left-hand earth banana plug at the top. So I'm curious whether we can read any voltage between the output of here and earth, because we are going to have a small amount of capacitive coupling between the core of the transformer and the secondary. So if we just move one of the jacks to the earth, so we're reading between here and here now. If we turn that on, so we are reading about 118 volts, probably at a very low current. We do have a low impedance measurement mode on the Fluke 289, so at the moment it's reading with possibly 10 meg input impedance. If we switch to the low impedance mode, we're just we're reading basically nothing here, 0.6 volts. So that all seems in order. I'm just going to take the cover off again and make sure the connections are nice and tight. I'll also put some hot glue just to support any of the to prevent any of the nuts working themselves loose on this on these banana jacks, and then we'll rivet the case closed. Okay, so just before we put on the cover to the transformer for the final time, we can just see we've got the line and neutral coming from the top cover running down here onto the IEC connectors. Here we have the incoming mains earth, the earth to the top cover, the earth here for the front stud, and the earth here for the core of the transformer. Now as we move on to the top cover, we've got our bundle of wires coming up along here. We have our mains earth connected to the banana plug at the bottom here, the earth one here, and that's also looped round and connected to the chassis on the top. We also have our earth, which comes only from the outlet IEC connectors, which connects to the earth on the socket at the top, and that then just only goes to this banana plug on the top here. And then finally we just have our two outputs from the transformer, which are looped into the 13 amp socket, and then those are the ones that are connected to the IEC connectors on the front panel. So everything's tightened up. I did tighten up all those connectors on the relay and on the timer that were rattling when the power switch was turned on. So we can now close the cover and we'll rivet the case closed. So we'll start putting in the pop rivets. And then we should just be able to use the pop rivet gun to close it up for good. So here's the final result. We've got the case nicely riveted closed. Hopefully we'll never have to open that again. We've got the labels which show what the two earth connectors do, so mains earth, output earth, and then we've got the two line outs. We've got 13 amp sockets on the front. If we do want mains earth on here, we can just link these two banana jacks out, and obviously we've still got our IEC connectors on the output. So that's really good now. I can use this on the bench without having to use all kinds of different leads to connect things together. Before I was using a 13 amp socket with a IEC plug on it, just plugging on here, and had plugged in my design under test here, but it was a bit of a faff with having all this cable. Much more handy just to be able to plug in the device here, or if I'm using the Hameg power meter, I can that has banana jacks on the front of it, so I can just use some straight leads straight into there if I want to do any power measurements. So I'm really happy with that. Hopefully coming up in the next week or two, I'll have a video on a new variac that I've purchased. Well, it's not new. I purchased it on eBay for around, I think it was £180. Unfortunately, it looks like the courier dropped it in transit, so the kind of the support bracket which holds the actual variac core broke. So I've taken it to pieces, and it's actually sheared the metal across here and on the side here. So for now I'm just seeing if I can fix this. I'll probably put a brace across here, and at the moment it's just got a bit of araldite across here. But I am in contact with the manufacturers to see if I can obtain that as a spare part. So at the moment the variac's kind of in pieces at the moment, and I've had to completely disassemble it to get the part that was broken out. It wasn't actually affecting operation, it just meant that the spindle was kind of on the wonk because it wasn't being held in place correctly. But hopefully we'll be able to get a spare part for that. This variac has a quick test type connector on the output, so you can insert your bare wires and that's how you get your output from here, but I'd also like to add 13 amp socket to this as well, and probably the banana jacks. Also, this has no soft start circuitry, so I think we'll design and build a soft starter for this and incorporate it within the casework hopefully, so that I can turn it on without risking tripping the MCB. So that should be in the next video in the next week or two hopefully. So thanks for watching.